Okay, in this lecture we're going to finish our section 11.6 material on the product and quotient rules. And in this second part of our lecture, we'll look at some applications of the product and quotient rules, and we'll see some more applications of derivatives in our next chapter, chapter 12, as well. But here's some simple applications similar to what we've already been considering, would be finding the equation of a tangent line to a curve at a given point. So let's look at some examples of this. In our first one, we are asked to find the equation of the tangent line to the graph of f of x is x to the 8th minus 2 times 6x minus 5 at the point 1, negative 1. So recall that there's two things that we need for the equation of a line. A point which the line passes through, which were already given in this problem, tangent line to the curve at our point 1, negative 1. And the other thing that we need for the equation of a line is the slope of that line. So specifically for the tangent line to the graph of a function, our slope is given by the derivative of that function. And looking at our function f of x, it is a product of two polynomials. So to find that slope, we could make use of the product rule. So let's start by saying, by the product rule, the slope of our tangent line, which I'll call m, is given by f prime of x, which is equal to, using the product rule, we take the derivative of our first function in the product, which would be 8x to the 7th, times the second function, which is 6x minus 5, plus the first function, x to the 8th minus 2, times the derivative of the second function, which is 6. Now here, we could either simplify this expression that we have for f prime, as we did in our earlier examples, or to save ourselves a little bit of work, we just need to find the value of the slope of this tangent line at the point 1, negative 1. So that is when the value of x is equal to positive 1, our slope m, which would be f prime of 1, is equal to, well, let's take a look at this. We have 8 times 6 minus 5 is 1, plus 1 minus 2 would be negative 1, times 6. And so we see we have 8 minus 6, or 2, for the slope of the tangent line to this curve at the indicated point, which has an x-coordinate of 1. So now that we have the slope of our line in a point that it passes through, we can use the point-slope form for the equation of a line to get our tangent line. So here we would have y minus the y-coordinate for our point on the line, which was negative 1. So we have y minus a negative 1, or y plus 1, is equal to our slope 2 times x minus the x-coordinate for our point, which was 1. So simplifying our equation and solving for y, we have y plus 1 is equal to 2x minus 2, or subtracting 1 from both sides, y is equal to 2x minus 3. So this would be the equation of our tangent line to the indicated curve at the point 1, negative 1. So now that we have use of the product rule, we can find tangent lines to curves which are products of functions. So let's look at another one. In this next example, we have a similar problem. Find the equation of the tangent line to the graph of f of x, which is a quotient of two functions, at the point 2, 1. So as with the previous example, we need to find the derivative of this function, which is the slope of the tangent line to this curve. And since our function is a quotient of two polynomials, we would be making use of the quotient rule. So by the quotient rule, our slope for the tangent line, which I'll call m, is given by the derivative of the function f prime of x. So using the quotient rule, we first differentiate the numerator. So the derivative of x is 1 times the denominator, which is x squared plus 2. And then we subtract the numerator, which is x times the derivative of the denominator, which is 2x. And then divide the entire expression by the denominator squared. So here, it's not too difficult to simplify this expression. We have f prime of x is equal to, we would have an x squared plus 2 minus 2x squared. So that leaves us with 2 minus x squared for our numerator over x squared plus 2 quantity squared for the denominator. So at the specific point of interest, the point 2, 1, x is equal to 2. And so our slope would be f prime of 2. So let's see what we have. Plugging in 2 for x here, our numerator is 2 minus 4. And our denominator would be 4 plus 2, which is 6 squared, or 36. So simplifying, we're left with negative 2 over 36, or negative 1 over 18. So now that we have the slope of our tangent line and a point that the line passes through, we can use the point slope form for the equation of a line to get the equation of our tangent line. So here we would have y minus 1 is equal to negative 1/18 times x minus 2. So simplifying, we have y minus 1 is equal to negative 1/18 x plus 2/18, or 1/9. And then adding 1 to both sides, we have y is equal to negative 1/18 x, and then 1 plus 1/9 would be 10 over 9. All right, so these two examples, similar to problems which we've looked at earlier in chapter 11, where we're finding the equation of the tangent line to a curve at a point, but we can now consider more complicated functions, which are products or quotients of polynomials. So let's look at our last example, an application in business. So here, let's recall some terminology that we had seen in chapter 3. So if the total cost of manufacturing X items is given by a cost function, capital C of X, recall that the average cost per item is the function denoted as C bar of X, which is found by taking our total cost, C of X, and dividing by the number of items that we produce, X. Now for a average cost function, we can define the marginal average cost as the derivative of that average cost function. That is C bar prime of X. So recall throughout this course, the term marginal is used to represent a rate of change. That's a term used by economists. So in our next example, we are given the following. The total cost in dollars to manufacture X mobile phones is given by the cost function C of X, which is a quotient of two polynomials plus 1,000. So in part A of this example, we are asked to find the average cost function. So recall that the average cost function, by definition, is the function C bar X, which is found by taking the total cost of producing X mobile phones and dividing by the number of phones produced, X. So if we take the given function for cost, C of X, and I divide through by x, I have x squared plus 2x plus 5 divided by my x plus 1 times x. So when I divide through by x, that's equivalent to multiplying the denominator by x. And then I have my plus 1,000, which we're also dividing by x to get our average cost. So simplifying this expression a little bit, I have c bar of x is equal to x squared plus 2x plus 5 divided by, if I distribute the x through my denominator, I have a denominator of x squared plus x, and then I have a plus 1,000 divided by x, which I could rewrite as 1,000 times x to the negative first power. So here my average cost function is the sum of two terms, where the first term is a quotient of two polynomials, and then I'm adding a 1,000x to the negative first on the end. So in part B, we are then asked to find the marginal average cost function. That is the derivative of the average cost function which we just found, and we see that since this first term in our average cost function involves a quotient, we need to make use of the quotient rule. So here our derivative, c bar prime of x, is found by first differentiating the numerator. So we have 2x plus 2 times our denominator, x squared plus x, and then we subtract the numerator, x squared plus 2x plus 5, times the derivative of our denominator, which is 2x plus 1. And then this whole expression is divided by the denominator, which was x squared plus x, quantity squared. Now on the end, we still have this 1,000x to the negative first term. So differentiating that, we would be left with a negative 1,000 x to the negative 2. All right, so let's simplify this expression a little bit, try to clean up the form of our answer. So in the numerator, if I expand and group like terms, let's see what I have. So expanding the product of these first two terms through the numerator, we have a 2x cubed plus 2x squared plus another 2x squared will leave me with a total of 4x squared plus 2 times x, and then I am subtracting the quantity. Well, if I expand the product of these two terms, I have 2x cubed plus x squared plus 4x squared plus 2x plus 10x plus 5. Still all over our denominator, which was x squared plus x quantity squared. And my term on the end, our negative 1,000x to the negative 2, I can rewrite as minus 1,000 divided by x squared. So in our last step, if we simplify the numerator, let's group like terms according to the power of x. So we see that we would have a 2x cubed minus 2x cubed will cancel. I had a 4x squared, and then I'm subtracting a 4x squared, so these terms will cancel. And I had a 2x, and I'm then subtracting 2x, so those terms cancel. And so I'm just left with, for my numerator, c bar prime of x is negative x squared minus 10x minus 5 all over our denominator, which was x squared plus x quantity squared, minus 1,000 divided by x squared. So this would be my marginal average cost function. And then in the last part of this example, part C, we are asked to find and interpret the marginal average cost at a production level of 500 phones. So at a production level of 500 phones, or when x is equal to 500, we have a marginal average cost, C bar prime of 500, of negative 0.004, and this would be dollars per phone. So our interpretation for this value would be the following. So at a production level of 500 phones, the marginal average cost, that is the rate of change of the average cost, is negative 0.004. So in dollars, that would correspond to 0.4 cents, or $0.004, so 0.4 cents. And the negative out in front indicates that our rate of change is decreasing. Our negative rate of change means that our average cost is decreasing the more phones that would be produced. So here our interpretation would be at a production level of 500, the marginal average cost is decreasing at a rate of $0.004 per